Hello 108 students, Mr. McHugh here with you on kind of like a bonus page for section 6.5. I appreciate you here watching this with me. I just want to try to convey how mathematics and algebra can be used in real life, and this graph of a parabola from the previous page where we had the rocket going up in the air. I asked myself, I wonder if you were going to solve this equation, h of t, t is time, you're given this quadratic equation. What if you solved it and you were told to set it equal to 0? Now, you know what's going on is, why do you set it equal to 0? That is where the graph crosses the x-axis. So here's your x and y axis. Here's x, here's y, and in this case, it's you're gonna see here on the graph, but something starts at the ground, it goes up, it comes down. Where it crosses, and of course when it hits the ground it's done, when it crosses the x-axis, which is time for us, and where it starts, that's called the solution or the roots. Okay, so when you set that equal to 0 and we take advantage of the zero factor property, find the two parentheses, the factors that work to produce the 0 here. Let's just work through the details here. I turn around, put 0 in here. I divided everything by negative 16 on both sides, and I got t squared minus 8t equals 0. Pulled out a t, GCF, left with t minus 8. Turn around and found the solutions where that here is 0 already. Solve this guy, t minus 8. Solve for it and you get 8, and this is t is in seconds. So does this make sense to you? The rocket starts off at time 0, and at time 8 seconds in it hit the ground. So what we're trying to say on this graph here, you know from that solution of the roots, ROTTS, that the rocket starts here at 0 on the ground, and when it was done 8 seconds later on the x-axis, 1, 2, 3, 4, 5, 6, 7, 8 seconds, it landed. Okay, so what I did here was I want you to get an appreciation of an expanded XY table. With this case we're talking about time and height. As time was 0, I substituted it in. 0 squared plus 128, the height is 0. It hasn't taken off yet. Okay, now you can follow the details here. You put it 2 seconds in, grind out the math, you find out that you're 192 feet. 1 second in, you're at 192, excuse me, 2 seconds, I apologize, 2 seconds. 1 second here, you're at 100 and, well, whatever this is, approximately, I didn't do them all. I don't know, 115 or something. So 3 seconds, you're at this height here. Notice what happened at 4 seconds. Notice 4 seconds is halfway between 0 and 8, and you hit your maximum height of 250. They could have asked you a problem and said, what will be the maximum height for this problem? This is one way to solve for it. We're going to learn some more later on when we get to chapter 9, but the vertex is where the maximum height or the minimum. The parabolas can also go like this, a bowl shaped, or they can go like this. Okay, so those aren't the greatest parabolas, and so that maximum height tells you at 4 seconds. So as you graph all these, you can kind of see here at 5 seconds where it was. Now what happens here in real life? The rocket gets shot off, it's loaded up with fuel, it's got a little bit of an angle, it's coming up here. The bad guys are picking a destination, and again, back at the Gulf War, they were shooting at Israel, they're picking cities, they were trying to use intimidation tactics. Now with the Aegis program, if we can get a ship close enough here, we can protect land-based sites because of the range of the rocket. Our missiles can come in here and intercept. For us to know when that maximum height is, the vertex, is crucial, because if we can shoot that rocket down before it gets there, it stops them from having multiple warheads come out. And so they load it up with fuel, they know it's going to get so far, run out of fuel, and then gravity does the rest on the downside. And that symmetry is always kept. I find this all very interesting. Okay, so for us in the Navy, if we could, our Aegis radar is on here, we would start tracking this rocket, and with a lot of fast calculations and computations, we would determine that quadratic equation. This is just want you to get appreciation of the computer program can figure out that calculation, then we got this guy. Meaning we know where he's going on his trajectory, and we'll know where the halfway point is, which we really want to get him before that. We now also know where they launched it from. Now that information is sent over there to our fighter jets, and they'll scramble them. They'll try to find those guys. A lot of these, if we can knock out that base, that eliminates more missiles being fired. Also, we know where they're shooting for now, and we could try to defend it. Okay, so I just want you to see and appreciate that parabolas have real-life applications. Mathematicians, engineers, scientists have all worked hard so that we can defend ourselves and fellow countries where threats are at. So, Mr. McHugh, I'm just going to sign off here now. We've finished up 6.5, which is good, and I appreciate you listening to me here and talking a little bit about parabolas and missiles and how that's got some real life applications. And I just say this in summary so you can appreciate how math is used as a language of order, and it's used to help solve problems. And you might not ever have to shoot down rockets, but it's good to know that our Navy and military are taking advantage of the mathematics to help us. Okay, that's all for now, so I'm going to sign off like I did here a couple minutes ago, and we have finished up Chapter 6.5 and Chapter 6. So I'm going to sign off here now, and next time I see you, we will start Chapter 7 with rational expressions and 7.1. Okay, so take care, and again, hopefully you went out and got a nice long walk and a longest day of the year, summer solstice. Okay, take care. Bye.